This is just to recapture what we have done on weak duality theorem. I've already stated this, and we also worked out a proof. Nevertheless, let me just reiterate one more time. If this is the primal problem, and suppose it's a minimization problem, and the other one is a maximization problem defined by the same problem data. This should be C, actually. Yeah. Where X is your feasible set defined by A and B, and W is your feasible set defined by A and C. If you have a feasible solution X and a feasible solution W for the dual, the objective value of the minimization problem, which is your Cx, is bounded below by the objective value of the other one, the maximization problem. Of course, the dual of the dual is primal, and you can also flip the roles of primal and dual. You can take one of them as being, you can take the dual as being the primal, the other one as being the dual, in which case, of course, if this becomes a minimization, the other one becomes a maximization, the same type of relationship still holds. The minimization objective value is always bounded below by the objective value of the maximization, even if you do flip the roles. Okay? All right, so the first corollary to this was if X bar is a feasible solution to the primal and W bar is a feasible solution to the dual, and if it so happens that the objective values are actually equal, if this is the situation, then X bar and W bar are both optimal to their respective problems. Okay, we already stated that. And corollary 2, what was corollary number 2? If one problem is unbounded, the other problem is infeasible. So if P is unbounded, then D is infeasible. And if the dual is unbounded, then the primal is infeasible. All right. These are immediate consequences of this relationship. The most important part here is the fact that X and W are both feasible to their problems. Okay? If you forget that fact, then everything goes wrong. So don't tell me that I haven't warned you. Okay? All right. Now, strong duality theorem. Well, before we go into the strong duality theorem, here are the possibilities. Maybe we should discuss that a little bit. It is possible that P is optimal and D is optimal, meaning that they both admit an optimal solution. Actually, if one, it will be the case that if one has an optimal solution, then the other one must also have an optimal solution. That's the strong duality theorem. The other possibility is that P could be unbounded, and in that case, D is infeasible. Or it is also possible that P is unbounded. Sorry, it's not that. If P is, say, infeasible, it is possible that D is unbounded. And it is also possible that P is infeasible when D is infeasible. So the infeasibility of one problem does not imply that the other problem is unbounded. Okay? The implication is one way. Unboundedness implies infeasibility, but infeasibility does not imply unboundedness. Infeasibility implies either unboundedness or infeasibility for the other problem. So if you look at the if you look at the implications, this is a one-way this is a two-way street. It's both ways implied. This one implies the other one is infeasible. Unboundedness implies P is infeasible. And let me change this one. Or let's just keep it this way. Infeasibility of one problem implies the other one is either infeasible or unbounded. Okay? So that's the implication for the last one. Okay. So let me go into the strong duality theorem. The strong duality theorem simply says that if you have a primal dual pair, and if it so happens that one of them has an optimal solution, so does the other one. Okay? And also their optimal values are equal. Okay. So let's work out a proof for this. I'm going to make use of the standard form primal and its dual to prove this, because that's the easiest way to prove. Of course, the statement actually applies to any primal dual pair, even though we work out the proof for a somewhat special case. Okay? So let's assume primal is, say, the minimization problem with ax equals b, x greater than or equal to 0. And the dual is the maximization problem with wb subject to wa less than or equal to c. No sign restriction on w due to equalities here. Okay? So use this primal dual pair for the proof. Okay? Assume, without loss of generality, that P has an optimal solution. Why is it without loss of generality? Because the roles of primal and dual can be interchanged. That's why. Okay? So we assume that one problem, in this case, P, has an optimal solution. We must prove that the other one also has an optimal solution. And we must also prove that the optimal objective values are equal. Okay? So, by the fundamental theorem of linear programming, whenever a problem has an optimal solution, it also has an optimal solution which is basic feasible, okay, or which is an extreme point solution. So then P has an optimal basic feasible solution. So I'm going to base my argument on an optimal basic feasible solution whose existence is guaranteed. So let's call that solution, say, x bar with basic and non-basic parts, xb and xm bar. Okay? Defined by a basis matrix, say B. Okay? Of course, B is a feasible basis matrix because by assumption xb, xn is optimal, which means it necessarily satisfies all the constraints. Okay? So let's define our W vector in a particular way. Let's define it by CB times B inverse. I'm using the same basis in inverted form. And so my claim is that W bar is actually optimal to the dual problem. To prove this claim, of course, you need to prove two things. Number one, you need to prove that it's feasible to its dual problem. Number two, its objective value cannot be any better. Okay? So, to prove feasibility of W to the dual problem, observe that the reduced costs associated with that is less than or equal to 0 for that particular basic solution. Okay? Because it's optimal. Okay? But we know that the reduced costs are defined by CB B inverse A minus C. And we just defined CB B inverse to be W. And we know that this is less than or equal to 0 because of the optimality. So that W bar times A minus C is less than or equal to 0 means W bar A is less than or equal to C. Okay? So it proves feasibility of W bar to the dual problem. To prove optimality, let's take the objective value defined by the solution on hand, x bar, which is Cx bar. That's your Cb xb bar plus Cn xn bar. Now the xn part is 0, so it just drops out. Xb part is Cb times B inverse B. Okay? And this part is, of course, your W by definition. That's how we proposed the solution. So this is simply W bar B. So I just showed that the objective value induced by the feasible or by the particular solution x bar is the same as the objective value induced by the feasible solution W bar. W bar is feasible, x bar is feasible, and because of the equality here, corollary 1 implies W bar is optimal to the dual problem. And of course, as a byproduct, you also get equality. Equality is just a byproduct of the entire thing. Okay? If you're not following, ask me now. I mean, it's quite straightforward, but nevertheless, some of you seem to have a puzzled look on your faces, so that's why I'm asking. Does anybody have difficulty following the argument? Okay, it's all clear. Fine. All right. Let's go to the next theorem now. Well, actually, let me begin here. The complementary slackness theorem. By the way, there's something quite eye-catching in this proof. What is it? The same basis defines an optimal solution for the primal problem via B inverse B. And it also defines an optimal solution to the dual problem via CB B inverse. It's the same basis that does the job for both problems. Okay? And that's, I think, something you should probably make a note of. All right, complementary slackness theorem. Suppose again you have a primal dual pair P and D, and you have a feasible pair of solutions. X is feasible to P, W is feasible to D. A necessary and sufficient condition for this pair of solutions to be optimal to their own problems is that they satisfy certain conditions that we call complementary slackness conditions. I'm going to state what those conditions are in a minute. Okay? So a necessary and sufficient condition that they both be optimal to their problems. Let's make these particular. Okay? Where's my W? Okay. A necessary and sufficient condition that they both be optimal to their problems is that they satisfy the following conditions. And these conditions are called complementary slackness conditions. If you take the ith variable in the dual problem, multiply it with aix minus bi. Ai is the ith row of the A matrix. X bar is the particular solution we have on hand. So the ith row times x bar is the left side of your ith constraint minus the right side of the same constraint. So this is simply the difference between the left and right sides of the ith primal constraint. This should be equal to 0 for every I. If you have, for example, m such constraints, this should be the situation. Okay? Similarly, if you take the jth primal variables and take the difference between the left and the right sides of the jth dual constraint, then that should be equal to 0. This should be true for each j going from 1 to n, assuming that you have n columns in your original A matrix. What is the left minus right side of the jth dual constraint? It's going to be the jth column. So it'll be the row vector W bar times the column AJ, the jth column of the A matrix, minus CJ. That's what you have. Okay? As I said, these are called the complementary slackness conditions. and they are necessary and sufficient for a given pair of solutions to be optimal. All right, so we need to prove this. So I'm going to use this time the canonical pair of problems. You know, I make it fit to my whichever particular form gives you the easiest proof, that's the one you use normally. So we use the canonical pair for the proof, meaning that the primal is a minimization problem of the form Cx subject to Ax greater or equal Bx greater than or equal to 0. And the dual is the maximization of Wb with Wa less than or equal to C and W greater than or equal to 0. So let's prove the necessity first. What am I supposed to show in necessity, or what do I assume in the necessity part? In the necessity part, we already know that X bar, W bar, they are feasible. We must show that if they are optimal, we must show that they necessarily satisfy the complementary slackness conditions. Okay? So assume X bar and W bar are optimal to P and D respectively. That's the assumption. We need to show that the complementary slackness conditions are satisfied. Okay, let's see how we can work this out. We have, by assumption, Ax bar minus B greater than or equal to 0, because X bar is feasible. We also have X bar non-negative due to feasibility. And we also have WA minus C less than or equal to 0 due to feasibility of W. And W bar is non-negative. So these are all given due to the assumptions of the theorem. So let's take this one. Let me multiply this. This is a column vector. Let me multiply this with a row vector W. So it's the dot product of a row vector with a column vector. Now what do we know about W? We know it's non-negative. And what do we know about this part? This part is greater than or equal to 0. So the entire thing will be greater than or equal to 0. Okay? Which implies, of course, W bar, Ax bar is greater than or equal to W bar B. That's what I have, just from the feasibility. And let's also take the other one, W bar A minus C, which we know is less than or equal to 0. Let's multiply this with X bar. So this is again a dot product. A row vector times a column vector. And I know x bar is non-negative. So the outcome of this will be less than or equal to 0. Okay? Which implies that WA x bar is less than or equal to Cx bar. Okay? So I've got the same stuff here, same left sides. It is greater than something in the first case, less than or equal to something else in the second case. Okay? So we have we have this inequality coming from the first one. Okay, I'm using this inequality here. And I know that the same thing is less than or equal to Cx bar. Okay. But by assumption, x bar and w bar are optimal, which means their objective values are necessarily the same. This is by the assumption of optimality and as a consequence of the strong duality theorem. Okay, we already know that. So the lower and upper bounds are the same. So this thing and this thing, sandwiches everything between. Okay, which means all inequalities above hold as equalities. All right, so we have equality which means W bar B is equal to W bar AX bar, which is equal to CX bar, which gives, what does it give? W bar times AX bar minus B is equal to 0. I'm just factoring W bar out from the left equality. So this is equal to 0. And it also implies W bar A minus C times X bar. This time you factor X bar out is equal to 0. Okay? That's the end of the proof. From there, you can get to the individual constraints on your own. Can everybody do that? Well, some of you seem to have a perplexed look. This is, well, what is this? This is, again, the dot product of a row vector with a column vector. So this simply says that you're talking about the sum of Wi bar, Ai x bar, minus Bi, right? The left side is a summation. I going from, say, 1 to m, if you have m constraints. So this summation is equal to 0. But what do you know about W? They are non-negative. What do you know about the parenthetical quantity? They are non-negative also. Aren't they? Yeah, they are non-negative. So each term here, the ith term, is a non-negative number. So you're adding up non-negative numbers to each other, and you obtain 0, which means every term must be necessarily 0. Okay? So this simply implies complementary, the first part of the complementary slackness conditions. Wi times Aix minus Bi equal to 0. The second one is similar. This is, again, a dot product, which is W bar aj minus cj times xj bar, j going from, say, 1 to n. That's equal to 0. In this case, xj is non-negative. This part is less than or equal to 0. So you're adding non-positive numbers to each other to obtain 0, which means every term must be necessarily 0. You have no cancellation of plus and minus terms. Okay? So again, this implies both of them together imply the complementary slackness conditions are satisfied. So that's the first part of the proof. Now let's go with the second part. So in the second part, we again have the feasible pair x bar and w bar, and we assume that the complementary slackness conditions hold. And we should show that x bar and w bar are optimal solutions. So the fact that the complementary slackness conditions hold imply w bar ax minus b is equal to 0. In other words, term by term, this is again a dot product, term by term, each term is 0, which means the dot product itself is 0. It's just the sum of all these terms, each of which is 0. And similarly, what else do we have? Again, the second part, w bar a minus c is, or when you take the dot product with column vector x bar, you again get 0, because each term of the dot product is 0 by assumption. So we have this one from the first, and we have this one from the second. And of course, they jointly imply that, well, WAX bar is equal to W bar B as well as CX bar. So W bar B equals CX bar. And so you have a feasible pair of solutions whose objective values are equal. And corollary 1 implies W bar and X bar are optimal to their problems. Okay? All right. So that's the complementary slackness theorem. Sometimes, if you look at the particular pair we have here, this is just a reinterpretation of the complementary slackness conditions in terms of the primal dual pair I have given you. So the primal is minimization of Cx subject to AIX minus BI. Sorry. AIX is greater than or equal to BI. So if I subtract a surplus variable, you get equality. Okay? This is surplus. And all original variables as well as surplus variables are non-negative. So I'm still using the canonical form primal dual pair, except that I made them standard form using my surplus variables. What is the dual? The dual is maximization of WB subject to Wij less than or equal to 0. So let's add a slack variable here. That's a j. By the way, of course, we have whatever for every I and for every j here. I going from 1 to m, j going from 1 to m. And of course, w as well as s is greater or equal to 0. Now, these are slacks. And in order not to confuse the surplus variables with the slack variables, let's just put a cap on top of your surplus variables. So, we distinguish them. Okay? Okay. So when you look at the complementary slackness conditions, what do they tell you? They tell you that the ith dual variable, if you look at the dual variables here, wi is associated with the ith primal constraint. So wi times aix minus bi in the canonical form is supposed to be equal to 0. But how much is this? It's Si cap, right? This is simply Si cap. Because Si cap, by definition, is equal to aix minus bi. So sometimes in books you will see that complementary slackness conditions are stated in this particular form. The dual variable associated with a constraint times the surplus or slack variable in that constraint, the product is equal to 0. Okay? Similarly, we have, what do we have? WA, sorry, yeah. W times AJ minus CJ times XJ. This is the jth primal variable, which is the dual variable associated with the jth dual constraint, is equal to 0 for every j. But the inside of the parentheses is simply Sj. Minus Sj? Okay, minus Sj, whatever. Doesn't really matter. Let's just write it the other way. It doesn't matter. You want 0, so it doesn't matter which one is minus, which one is plus. So Sj, that's going to be Sj, which means Xj times Sj is equal to 0 for every j. All right, here's a question for you. If xj is a non-basic variable in an optimal solution, for example, xj is 0, so sj can be positive, which means that whenever you have non-basic variables under consideration from the primal problem, the associated dual constraint can hold as a inequality, strict inequality. How about here? Or let's just continue here. If xj is basic, assume non-degenerate, so it's positive. In that case, of course, sj is necessarily 0, which means that every primal variable which is positive in a basic feasible solution will give a dual constraint which holds as equality, which will be active. Similar interpretation can be also given here. So let me stop here. Let's take a 10-minute break and then we continue. Okay?